Okay, this lecture is going to be over problem 4.9 here in Bentel's chapter 4 text. So what I want to do is I want to work through this particular problem to kind of show you exactly how it's done. So you got a cobalt 60 beam and you've got a dose of 180 centigrade that's prescribed in the mid plane of the brain. So the parallel opposed lateral cobalt 60 fields are going to be used. The lateral diameter of the head is 14 cm. Now, since this is going to be a whole brain, let me kind of show you what it is that we're going to be talking about here. So we got patient here lying on the table, and we're looking down through the top of their head. So we're going to have a beam over here on this side, and then we're going to have a beam over here on this side. So now the top of the head from here over to here, that measurement is going to be 14 cm. So if we're going to be treating midplane, which is roughly right about here, we're going to cover half the distance. So we're going to split this up, and we're going to 7 cm here and 7 cm over here. Now, the field size is going to be a 17 by 23. And the SSD is going to be 80. So the dose rate for a 10 by 10 field is going to be 107.3 cm, and the area factor is going to be 1.047. In other words, this is the dose rate we would see if we just had a 10 by 10, but since we have a 17 by 23, this is where we're going to end up seeing. So what's the treatment time required to deliver this treatment? Well, let's take a look at this. What we are going to need is we are going to have the dose delivered by the beam. And since these are equally weighted, we're going to have that. And then we're going to have the dose rate at the reference multiplied by the area factor multiplied by the PDD. Now, we don't exactly know yet what the PDD is. That's something that we get to look up. So we know that the dose rate at the dose that's going to be deposited by one of the beams, since they're equally weighted, is going to take that 180 and we're going to cut it. 180 centigrade, and we're going to cut that in half. And so we're going to have 90 centigrade delivered there to the midplane. So we know the dose delivered by one beam is going to be 90 centigrade. We also know that the dose rate for the reference field is going to be 107.3 centigrade per minute. And what we're going to see here is that these two units cancel out. The min, since that is in the denominator down here, it'll end up being in the numerator later on. So we're going to multiply that by 1.047 to account for the fact that we have a larger field than a 10 by 10. We now need the PDD. Now that's going to be the tough spot here. It says to go and to look at table A.1 for the PDD. We have a 17 by 23. If we go and if we look eventually at this table, we're going to see that we've got square fields up here, and we don't have anything close to the 17 by the 23. So what we get to do is we get to figure out exactly what the square field for that would be. We're going to use this particular formula right here. So we're going to go back here, and over on this side, which I'm going to go ahead and get this re-engaged, we're going to take 17 by 23 and multiply that by 2 times the sum of those two. So 17 by 23, if you multiply that out, end up with 391. And that's going to be divided by 2 times 40. So in the end, that's going to be 4.8875. Now that's not going to be the field size. Remember, that is going to be the area divided by the perimeter. If we want to know what the area is, what we're going to do is you can do this one of 2 ways. Let me show you the easy way. We know that this ratio is equal to that. What we also know is that this formula, where this comes from, if you condense it down, ends up being not 4 divided by a, but a divided by 4, right? Let's make sure I got this correct. A divided by 4. So I need to go here. And then go here. So I know that 4.8875 is equal to a divided by 4. That means the side of the square field that this is equal to is 4 times 4.8875. That means a is going to be equal to 19.55. That's not on the table. So what do we do? How do we still use this? Because we've got to be able to use it somehow, right? Now, if you go to the Bentel listing that I have for this, you can find the appendix on this, and table A1 will be there. So somehow we've got to figure out how in the world we're going to interpolate between 18 and 20. What we've also got to figure out is what's the depth. How do we know what the depth is? Well, the depth in this case is, since we are treating this at midline or mid-plane, it's going to be at 7 cm. So we got that part figured out. So what we need to do is we need to figure out what value we choose here between 71.6 and 72.2. Now, in order to be able to do that, here's what we do. I want to figure out how far we are in, since we're at 19.55, we're going to be closer to this value than we are this one. But the question is, how close? So I know that if I take, and so get this re-engaged. Okay. So I'm going to take most of this out so we've got room to work. But we've got that value down there we can work with. So we're doing good. All right, so now we'll put this back on. So I know that we've got 19.55 is our length. If I take that, and I know the distance, or the difference of the distances here between 18 and 20, it's going to end up being 2. I know here that this is at least 18, but it's not quite close to 20. The question is the minus 18. That leaves me with 1.55. Question is, how far over here am I from being over here? If I take 1.55 and I divide it by 2, what do I come up with? I get 0.775. Now you might be thinking, well, goodness gracious, where did this come from again? Again, I know that the distance between 18 and 20, that distance here is going to be 2. I know that right now, since I'm sitting at 19.55 as a length, if I subtract out 18, I know I'm at 1.55. This tells me I'm a little over 77% to the way over to 20 from 18. Why is that relevant? Well, what I'm going to do next is I'm going to say, okay, at 7, what is the distance between 18 and 20? The distance there, or the difference between the PDDs, is this. So I know that the PDD is going to increase a little bit here as we go from 18 to 20. Question is how much? Well, I know that I'm going to start at 71.6, and then I'm going to take this factor that I found, 0.775, multiplied by 0.6, and that tells me what my new PDD is. So if I take 0.775 multiplied by 0.6, and then add that to 71.6, I come up with 72.065. That's going to be my PDD. So when I go over here, I'm going to multiply this by, and I'm going to convert this to a decimal, 0.72065. I know the book would go through and probably multiply by 100 here and leave this as a 72.065, but I'm going to do it this way because it tends to kind of make things a little easier. So now that I have all of that, I'm going to scoot down here just a little bit, put this back on. So I'm going to go here. I'm going to say, okay. I know I've got 90 centigrade on the top. Question is, what do I have down here? I'm going to take 107, and I guess I should use calculator here. Okay. So I'm going to take 107.3 multiplied by 1.047 multiplied by 0.72065. So that's going to be my number, 80.96. Now I'm going to use a small little trick here that sometimes helps, because I've got to take this number and I've got to divide it into 90. So just for the sake of bookkeeping here, I will show you that this is going to be 80.960 centigrade per minute. Now I need to fix that and make that into the number of minutes that we have here. And I'll show you a little trick to do that. If I take 80.960, I know that's the denominator down here. And guess what? I'm going to tell the calculator that that's my denominator. The way I do that is I say, I'm going to call this 1 over x. And now all I have to do is multiply that by the numerator. Basically, I'm finding a reciprocal of it. So you can see here 90 times 1 over this stuff, and that's what this turns out to be. So now I'm going to move this over here. I'm going to take this, give me a little room here, back to drawing because I enjoy drawing. So I end up with 1.1117 minutes. Now it's asking me for the number of seconds here. So basically I'm going to strip off anything over here that's to the right, I'm sorry, to the left of the decimal point. So it leaves me a 0.1117, which over here, all I would have to do in the calculator is subtract 1 in this case, and that gives me the decimal right here, and then multiply that by 60. And when I do that, it gives me 6.699 seconds. So this right here, this gobbledygook, is going to be equal to 6.699 seconds. Another way to write this is to say this is 1 minute and 7 seconds. So in this particular problem, what we figured out the time. That's what it was asking us to do. And we had to do a little interpolation on that table that was in the back. And we had to multiply the other factors together. I hope that this video was instructional for you, and I will work some more problems here as we go along, because I want to make this as clear to you as possible.